So today we are looking at the next bit, which is graphing rational functions. So we've already done some graphing of rational functions. And today, now we know some calculus, we're going to be able to, any turning points that there might be, we'll be able to find their locations. Alright, so graphing rational functions. Alright, so you might have to, like, addition of ordinates you can use as well for doing this. So before I get to the finding of the turning points, so one technique, of course, would be addition of ordinates. So you can use that when you have a graph. Have graphs of the individual parts. And so, of course, for each x value, you have the y values together. Alright, so this example here that I'm doing is one very, very similar to something that was on a recent exam. It was structured differently to this. In that there was a part before this particular bit. So fx equals x squared plus 1 over x, given the graphs of y equals x and y equals 1 on x. Alright, so if we have a look at those two graphs, y equals x looks like this. So y equals x, it's wobbly, but anyway. So that's y equals x. 1 on x looks like this. And then we've got to draw x squared plus 1 over x given these two things. Now, the part on the exam, the part of the question that came before you were asked to sketch the graph was you were asked to show that x squared plus 1 over x was the same as x plus 1 on x. That's what you were asked to show. You were asked to show that these two things were equivalent. That was part A, and then part B was to do the sketching. All right, so there's a number of different ways you could show that. And one of the ways that you could show that, doesn't matter which one, I can say, all right, that fx is equal to split this up into two parts, plus 1 on x. Here we've got some cancelling, so we end up with x plus 1 on x. All right, so in the exam question that was part 1, and then part 2 was to then sketch. So it's saying plus, so that means that we, different colour, we need to add for each x value, we add the two y values together. And so when we do that, green plus blue, green plus blue, green plus blue, and so on. So you get something that looks like that. And over here, green plus blue, and you get the same kind of thing. Like that. So the red one is fx equals x squared plus 1 over x. Alright, so we've got some stationary points there and there, but this addition of ordinates is not going to tell us exactly where they are. But if we want to find exactly where they are, we can do that, because the gradient at those 2 points there would be 0. Gradient of the curve at here and here, yeah. 0, yeah? All right. Or any points of inflection that there might be as well. So let's have a look at where, if there are any. So this method doesn't tell us the exact location, so this method doesn't tell us the exact location. Stationary points, turning points, points of inflection. All right, so if we want to find them, we need to use the derivative. So we need to use calculus. And so for, I'll leave that graph there and work around the graph. So for turning points, f dashed x equals 0, and for points of inflection, second derivative would be equal to 0. So it doesn't matter which version that you look for, but on the version I'm going to use the x plus 1 on x bit. So that's easier for me to differentiate. So rewrite 1 on x as x to the minus 1. So the first derivative minus 1 on x squared. And if that equals 0, so for our turning point, f dash x is 0, so 1 minus 1 on x squared equals 0. So 1 would be 1 on x squared, I hope. X squared equal 1. Yes? No? Maybe? So we've got two possibilities there. So x could be equal to 1, or x could be minus 1. And that looks, we've got 2 here, so that makes sense for us. So we need to find out what the y value was. So f of 1 would be 1 plus 1 on 1 is 2. So that means that the coordinate of this point here, that coordinate there is 1 and 2. And this coordinate here is going to be negative 1 and something. And so f of negative 1 is negative 1 plus 1 on negative 1, which should be negative 2, I believe. Alright, so now we can find those points. And there may or may not be some points of inflection, and we would need to look at the second derivative for that. So here's our first derivative. We would need to find our second derivative. So let me do that up over here. So our second derivative, so for our first derivative, and I'll write the index form 1. So 1 minus x to the minus 2. Differentiate that again. F double dashed x. 1 becomes 0. Bring the power down, so it's positive 2x to the minus 3, which of course can be written as 2 on x cubed. Now, points of inflection would occur when f double dashed x is equal to 0. So, can that be the case? Can f double dashed x equal 0? So, in other words, can 2 on x cubed equal 0? No, it can't, can it? Alright, so here there's no solution. So for this one here, there's no point of inflection. Alright. Interesting examples here with this. Very interesting examples. Alright. Alright, I've got 3 more examples. Alright, so let's sketch y equals x cubed plus 2 on x, and x is not allowed to equal 0. Alright, so let's first of all look at some asymptotes. The first asymptote that there is already revealed itself. So if x is not allowed to equal 0, we've got a vertical asymptote. Is x equals 0. To find any other asymptotes, we need to rearrange this. So if I've got y equals x cubed plus 2 on x, if I rewrite that as x cubed on x plus 2 on x, over here we've got some cancelling that can happen, and so we've got x squared plus 2 on x. So the other asymptote, we've already got one asymptote, x equals 0. That's relating to this part. The other asymptote relates to the other stuff. Now, the other stuff in this case is x squared. So the other asymptote is x squared, which is quite interesting. So we've got an asymptote that's curving. All right, let's have a look. All right. Intercepts. Y-intercept. X equals 0. And so from that we know that there is
one.
There isn't one because it's an asymptote, isn't it? X equals 0. So there's no y-intercept. All right. So no point us even worrying about that. X-intercept. Y equals 0. So let's use this version. So 0 equals x cubed plus 2 over x.
Does it matter which version you use?
No, it doesn't matter which version you use. You'll get the same answer. I don't use that version just because I think it might be easier, but it may not be easier. Times both sides by x, you get 0 equals x cubed plus 2. Take 2. So x is the cubed root of -2. Alright, so let's have a look at some information that we've got so far. So we know we've got an intercept here. Sorry, an asymptote here. So that kind of asymptotic behaviour. Also, somehow or other, y equals x squared is going to become involved in it. It's the other asymptote, somewhere or how or other. We know we haven't got a y-intercept, but we've got an x-intercept at the cube root of -2. And so the cube root of -2 is about here somewhere. So that's cube root of -2 and 0. And so we need to find some other stuff. Alright, so this might be going like that, for example. Alright, but over here we've got no kind of information where the curve might go over here, so we need to find some other stuff. So other stuff that we can find, of course, are turning points, stationary points, and points of inflection. Alright, so stationary points. The derivative equaling 0, first derivative equaling 0. Well, I should use the right notation. Should use dy dx, given that's what we've got in the question. So dy y dx equals 0. And because I've prepared one earlier, the derivative of this if you use this version, you find that the derivative is 2x minus 2 on x squared. Alright, and y dx has got to be equal to 0. 2x minus 2 on x squared. Got that x squared down the bottom here. It'd be nice if we didn't have that. So how can we get rid of it? Times everything by x squared. So over here we've still got 0. This one now we've got 2x cubed times 2. Let's add 2. Let's then divide by 2. And so the cubed root of 1, and the cubed root of 1 is? 1, yes. Alright, so if we now go and substitute that back into one of these, so y will be 1 cubed plus 2 over 1, which is?
I just replaced the spitting out the hundreds of...
What's that? Okay.
Nothing.
1 cubed plus 2 divided by 1?
3.
3. So at 1 and 3, what do we have?
Stationary point.
A stationary point. Correct.
Would that be a turning point?
What do you think? What do you reckon?
Yeah.
So 1 and 3 is going to be there somewhere.
It would be.
It would be, wouldn't it? So what we're thinking is this is going to come down around like that, yeah?
Yeah.
Yep. So there's one part. So we've got another part over here. Question is, are there any points of inflection? I'm going to rub this stuff off here. Are there any points of inflection? So to find points of inflection, if there is any, it's the second derivative, d2y dx squared, to be equal to 0. And because I've prepared one earlier, the second derivative is 2 plus 4 on x cubed. Alright, make that equal to 0. We've got that x cubed down there, so if we use the same strategy, times and everything by x cubed. They cancel. 0 equals 2x cubed plus 4. Take 4. Divide by 2. So x would be the cubed root of -2. And we've seen that before? We have.
Yeah.
Where have we seen that? It was the x-intercept, wasn't it? So the x-intercept here happens to be my point of inflection. So I said it's going to go something like that. So it's going to swing around here and then, whoops, a bit closer to the asymptote would be nice, something like that.
Is that all?
For that one, yeah. All right, any questions about that? No? All right, next one. Very nice. This one, you're going to love it.
You always say that.
God, don't you believe me? That you're not going to love it. All right, any questions about that? All right, you know how to do all of that stuff. You just got to be patient and work through it. All right. So the next one is going to have two vertical asymptotes. So if we've got this, for example, we're going to sketch the function. And the domain of this function is the real numbers except for 0 and 1. So already that kind of suggests something. If the domain doesn't include 0 and 4, that suggests that something's going to be going on at 0 and 4. All right, so let's have a look at the function. So 1 on x squared minus 4x is our function. So if you look at our function, which is 1 on x squared minus 4x, we can factorise that denominator, take x out as a common factor. We've got x and x minus 4. So when we look back at our domain that I already said, we're excluding 0 and 4 because something's going on. Well, when 0 and 4 is undefined, isn't it? So that means we've got how many asymptotes? 2. 2 vertical asymptotes. So vertical asymptotes. X equals 0 and x equals 4. So if I'm going to draw that particular graph, then I've got one here, one here, horizontal asymptote, or other asymptote. In this case it's horizontal, I believe. So from what we know, where would our other asymptote be, do you think? All right, let's think about it another way then. So as x goes towards infinity, what's going to happen to f of x? 1 over infinity squared minus 4 lots of infinity. So 1 over infinity squared minus 4 lots of infinity, what's that? Big number, massive, huge, gigantic number. And 1 over a massive, huge, gigantic number is a teeny tiny number.
Yeah.
So that's going towards 0, isn't it? And as x goes towards negative infinity, fx goes towards, I should say, rather than equals, goes towards 1 over negative infinity squared minus 4 lots of negative infinity. So on the bottom there, again, huge, gigantic, massive, big number. So 1 over a massive number is a teeny tiny number, so again that's going towards 0. So our other asymptote then is our x-axis. All right. So now we've got this broken up into 6 sections, and we now need to know whereabouts the stuff might be. So one thing that we can do, so it's likely that in the middle here it's going to curve like that, so it's likely that in the middle there's going to be a stationary point. So let's find it out if there is one. So for stationary points, turning points, the derivative of course is 0. Alright, because I've prepared one earlier, the derivative. So sorry, I've prepared one earlier. The derivative is, just to save time, I'm going to just write what it is. So if you use the quotient rule, right, use the quotient rule, that's what you end up with. Alright, and now we need to solve that equals 0. So if that equals 0, times both sides by x squared minus 4x all squared. You got that? Take 4. Divide by -2. X equals 2. To find what y is, or the fx value is, we then want to know what f of 2 is. Now remember the original equation was 1 over, so our original was 1 over x squared minus 4x. So we've got 1 over 2 squared, 2 squared minus 4 times 2, 1 over 4 minus 8, which is 1 over -4, which is -1/4, I believe. So at 2 and -1/4, so that would be down there, wouldn't it? All right, so got that curve in there. Over here, where do you think the bit of the graph would be?
The top.
Up the top, yeah. Is up the top. You can check that if you like by just picking an x value. All right. And over here,
Wait, do you have to find a point for that top?
maybe, depends, you need to be guided by the question. But yeah, might not be a bad idea to find a point.
So you just say like x equals 5 and then find.
Use 5, yeah, and find a point, yep. So if we use 5, what do you got?
Got 1 over 25 minus 20.
Yeah, so a fifth.
Yeah.
Yep. So here we go, got that point in. So this point here is 2 and -1/4. That point there is 5 and 1/5. And then you can do the same over here. And when you do the same over there, you'll get that.
So we don't need to find the points in
And
the
again,
question.
you can find a point. So put -1 in. Right, so negative 1. 1 over negative 1 squared minus 4 times negative 1. 1 over 1 plus 4 is a fifth again. Yeah? So you know that it goes there like so. All right. Got one more example. So sometimes there's some very interesting stuff goes on. That was reasonably interesting. This next one is going to be even more interesting.
Here, this is the last example.
This is the last example, yeah. Now, in the interests of time, I'm going to probably not go through the differentiations, particularly the second derivative, because it's but you can look at my working later if you like. All right, so e.g. on sketch, y equals 4x squared plus 2 over x squared plus 1.
Looks like one.
All right. So let's go some asymptotes to start off with. So for vertical asymptotes, we would look at this here. All right. And so we can't have 0 on the bottom, can we? So for our vertical asymptote, we're looking that when x squared plus 1 equals 0. Now, what do you know about x squared plus 1 equals 0? X squared equals negative 1.
Yeah, so
X would be square root of negative 1.
plus.
No real solution. So in terms of this graph, it means there is
Yeah.
no asymptote here.
No asymptote.
No. Because it would be at, the asymptote would be at x equals the square root of negative 1. In the real number field, there isn't, is there? All right, so no real solution. So that means no vertical asymptote. All right, is there a horizontal one? Well, let's, or an other one. So the way that we can look at that is this particular way. That is what I did before. So as x goes towards infinity, y is going to go towards 4 lots of infinity squared plus 2 over infinity squared plus 1. Now, the plus 1 and the plus 2 on the end is insignificant. All right, so it's actually going towards 4 lots of infinity squared over infinity squared. The infinity squareds kind of cancel each other out in the end. Well, we've got this 4 up here. So it's going towards 4.
I have trouble getting up.
Does that kind of make some sort of...
Yeah.
And so if we went negative infinity, we had the same kind of thing. We'd have 4 lots of negative infinity squared plus 2 over negative infinity squared plus 1. Again, the plus 1 and plus 2 are insignificant. When we square a negative number, we get a positive. So again, that's going towards 4. So whichever way we go, we're going towards 4. So that indicates that we have asymptote at y equals 4. Right, that's one way to do it. You could divide that out as well. If you divided this divided by that, you would find it's 4 as well. Alright, so that's just another technique that you can use. Alright, so far what do we got? So far we've got this. Here at 4, we've got an asymptote. So far. Alright. Let's see if we've got any intercepts. Can I rub this stuff off? Let's see if we've got any intercepts. Let's do the y-intercept first, that's the easy bit. Y-intercept x equals 0. So y would be 4 times 0 squared plus 2 over 0 squared plus 1, which would be
1 over
2, yes?
Yeah.
So we know we've got an intercept here at 2. Let's look at x-intercepts. Y equals 0. So 0 equals 4x squared plus 2 on x squared plus 1. Which hopefully then goes to that. Take 2, divide by 4, and
Would you need the plus or
You can't do
minus?
that either.
can't do that either. Yep. Sorry, what did I do?
No, nothing. Don't worry.
Yeah, can't do that. So we're trying to square root a negative number, which then,
So there's no x-intercept.
no x-intercept. Alright, so no x-intercept. So what else did we know now before from what else that we knew? So we know it goes through there. We know it goes through there. We know when we go up that way we're going towards 4. We know when we go this way we're going towards 4. Question is what happens in the middle. So let's see if there's any stationary points. Can I rub that off?
Yeah.
Now let's have a look at stationary points. Alright, so stationary points, dy dx equals 0. Alright, so if you use quotient rule on that, use the quotient rule on that, you get this. For x over x squared plus 1 squared. Alright, so quotient rule, I'm not going to go through that, you know how to do that. Alright, so we're going to make that equal 0, so 0 equals 4x over x squared plus 1 squared. times both sides by that denominator. X is,
0.
have we seen that before?
Turning point.
It's a turning point at
Y
y equals 2, yeah. So x equals 0 is our y-intercept. So it looks like... So it looks like we're going like this. Now if we're going like that, then there's probably some points of inflection. So, let's have a look, see if there is. So points of inflection would be the second derivative equals 0, and second derivative, lots of working out there doing the second derivative.
Do you want to show?
But when you end up with this. Because there's some cancelling out stuff that goes on during it. So you would be expecting that bottom here would be power of 4. Right, so one you've got to square something that's already square. But there's some cancelling that goes on. You can have a look at my working if you want. I'm saving this much stuff, right? All right, so if we make that equal 0, times both sides. I'm going to move the 12x squared over. Divide by 12, so that's a third. Plus or minus the square root of a third. And then I haven't worked out the y value. Why haven't I done that? So, which of course you're probably going to see that plus or minus root 3 on 3 when we rationalise the denominator. Yes? So one of them's down here, negative root 3 on 3, and root 3 on 3, and you whack that into this to find out what your y value is, which I can't be bothered doing at the moment. Do you want me to do it?
Yep.
I didn't write it down. You do want me to do it. Of course you want me to do it.
Put it in the calculator.
Oh, yeah, well, I'll just put it in the calculator. So y would be 4 lots of 1 on root 3 squared, which is 1 on root 3. Here's 1/3. Plus 2, it's not as bad as I thought. 1/3 plus 1. So 4/3 plus 2 over 1/3 plus 1. 2 is 6/3 plus 4 is 10/3. 1 is 3/3 plus 1 is 4/3. Dividing by fraction, flip it over and multiply. 5/2. There we go. That point there is root 3 on 3 and 5/2. And this one here is root 3 on 3 negative and 5/2.
Wait, are they meant to be root 3 on 3 instead of 1/3?
So, square root of 1 is 1 root 3 times bottom by...
No, when in your equation for y.
I've squared it.
Oh, okay.
So when I've squared it, here is x squared here. It's 1/3. Taking a shortcut. Right, there we are. See, I told you it was fun.
Can
Righto.
I have a look at your working out?
Question set number 7.
Thanks. Oh my gosh.
See, I told you.